Hello, statistics students. Welcome to section 7.3. 7.3 is called confidence intervals and sample size for proportions. So in 7.1, we did confidence intervals and sample size for population mean, right? In section 7.2, we did population mean, but it was when we didn't know sigma. And in section 7.3, we're going to make confidence intervals for proportions. We've done proportions before, so let's talk about what we need to know. So for an example, a recent USA Today snapshot stated that the percentage of respondents who have walked into someone while texting is 36%. I would say that's higher, but so 36% represents a proportion or a population parameter of cell phone users. That is our P, right? Our probability of success, if that's how you're thinking of it still. But it's for the population. Sample size was 738, so that's our N. The proportion represents the part of the whole group and can be represented as a fraction, a decimal, or a percentage, or represent a probability. So we would say that P is equal to 0.36, or perhaps you'd go with 36 over 100 and definitely simplify that. But we can say that either way, or the probability that someone walks into someone while texting is 36% probability. So we've got some symbols to talk about, and they're going to feel familiar. We're going to add to them. We already know that P is the population proportion. It's the probability of success, but the important part here is that it is from the population. This is always going to be in the center of our confidence interval. The first two sections we were talking about mu, or the population mean. Now we're going to be talking and estimating the population proportion. P hat. So it's literally a P with a little arrow-ish above it. We call it P hat. This is the sample proportion. So this is what we can actually calculate or find because it's from a sample. If we need to figure out a formula, so in that last page, we knew that P hat, or we could say that P hat could be, say, 37% or something like that if we take a sample. If we need to calculate P hat, it's equal to X over N. So X, I'll say in a minute, is whatever characteristic, the number of sample items that have the characteristic, over N, the sample size. Q hat, just like every P and Q, P hat and Q hat go together. I like this one best. If you've already calculated P hat, why not just go with Q hat is equal to 1 minus P hat, right? Because P and Q, even if they're wearing hats, add up to 1. If we were going to do the formula, we could say the sample size minus the number of variables that were successes over the sample size. So basically, we're saying the number of failures over sample size. X is the number of sample units that have what we're looking for, the number of people in our sample that have walked into someone while texting, and who can forget that N is equal to sample size. If you want over here, I don't know if you like a little reminder that P hat plus Q hat equal 1, just like P and Q equal 1. All right, so let's do a little bit of finding P hats here. So example 7.7, find the sample proportion and its complement. So the sample proportion is P hat, the complement is Q hat. They add up to 1. They're opposite sides of the same thing. So N is 80, our sample size, and X, the number of items from that sample of 80 that have what we're looking for, is 45. So P hat will be equal to 45 over 80, right? X over N. I believe that's approximately 5625. We could do, well, the other 35 items out of 80 when we find Q hat. I prefer to just do Q hat is equal to 1 minus 5625. So that would be something like a 4375. Double check my math because you know how this goes. Some days are better than others. I wanted to give you a simple example for part B where the work's already done for you. Somebody already calculated for 39% find p hat and q hat. Well, just like that texting example, p hat is already given. So that's our 39%, 39 over 100, however you want to write that. And then we know that we can do a quick calculation. Q hat is equal to 1 minus that 0.39, so that's probably something like 6.1. Seems simple, right? So p hat and q hat, are items that we're going to need to be able to calculate for our confidence interval for finding sample size. So find the sample proportion, its complement. 200 people were surveyed on if they're satisfied with their current job. 162 said they were satisfied. Find p hat and q hat. P hat is the proportion of people satisfied. So this is success, right? Is if they are satisfied. So p hat is going to be equal to how many people are satisfied over how many people were in that sample. So 162 out of 200. So that's probably about a 0.81. And then everybody knows how to find q hat. We could say that it was the other 38 people out of 200 and calculate it who were not satisfied with their job. If you want to do it that way, go ahead. Otherwise, go this route and say it's a 0.19. All right, just the basics. So now let's talk about confidence intervals. So we're going to use p hats and we're going to use proportions. So confidence interval for a proportion, the first thing that you need to know, make yourself a little mental note. P for population proportion is always the parameter that we're looking for, and we're estimating and we're saying it's in this interval with 95% confidence. So P will always be in the middle. This is the first difference between the first two sections. So the first thing we should mention is the margin of error. So this is what we're going to add and subtract from our p hat. So the margin of error is z of alpha over 2. So we go to which table, the pink or the yellow, right? The pink table, because that's our z table. And then it looks a little messier. It's a giant square root of p hat times q hat over n. So again, probably the hardest part once we get all our numbers is going to be doing the calculations. Do a quick check. Make sure that n times p hat and n times q hat are both greater than or equal to 5. This is back, if you remember, from section 6.4, where we had to verify that it was relatively normal. So that is a check to see if normal. And last but not least, we got to work on the rounding because I haven't been as strict about it as I should be. Round to 3 decimal places. So this is important. Make sure you've got that formula. Our margin of error is what we add and subtract on both sides of that interval. All right, you ready for the formula? So our formula for a confidence interval for a proportion. I know I keep saying it over and over again, but please notice in the center of this interval is P for population proportion. That's what we're estimating, or that's what we're making an interval for. So it's P hat minus that margin of error, z of alpha over 2 times the square root p hat q hat over n. And then on the other side of that interval, it's p hat plus our z value times the square root of p hat times q hat over n. So technically, if you like to shorten things up, it's p hat plus and minus our margin of error. Make sure that you put proportion, population proportion, in the center of your interval. So I'm hoping that this feels very familiar, still finding z values, a little bit of different calculations to find p hat and q hat instead of x bars and sigmas or s's. All right, so let's do an example. Nursing applicants. A sample of 500 nursing applicants included 75 from men. Find the 90% confidence level of the true proportion of men who applied to the nursing program. So that way to ask the question, find the 90% confidence level of the true proportion. That tells me that P is going to be in the middle of that. It's not the confidence level of the true mean of blah, blah, blah. So let's jot a few things down over here, things we're going to need to know. We'll need to know N sample size. We'll need to know P hat and Q hat. We will probably need to know a Z of alpha over 2, and that might be it for that formula. So jot down what you know. I mean, the easiest one, right? A sample of 500 nursing applicants. Included 75 from men. So our P hat is going to be the number of successes. This is about how many men, so 75 over 500 was the sample proportion. So I think that's about a 0.15. So Q hat, I'm going to do some quick math here. So that means Q hat is the probability of not success or failure in this sample. In this case, that's how many women were applicants. So that would be the other 425 out of 500, or use the complement and say that's a 0.85. And last but not least, our Z of alpha over 2, it's a 90% confidence level. So alpha equals 10%. So alpha over 2 equals 5%, which is also equal to 0.0500. Everybody's jumping into their Z table right now, I'm sure of it, and searching for an 0500. That is a betweener, I think. It ends up being a 1.65. So now we're ready to set up our proportion. So it's P hat minus the Z of alpha over 2 times that giant square root of P hat Q hat over N. And then the same thing with a plus on the other side. So I'm going to start with my P hat, 0.15 minus my Z value, 1.65, a giant square root. Up here, I'm going to have to put in a 0.15 times a 0.85. That's my P hat times Q hat over my sample size, 500. Again, the calculation could probably be the hardest part. I do, without the radical, I do the 0.15 times the 0.85 divide by 500. I then take the square root of the answer, and then I do my multiply that by 1.65 and go from there. So I do that radical part first. Do whatever makes sense to you. Just be careful when you do this problem. Please make sure you do this problem to make sure you get the same answer. So let's see, for the rest of this then, I'm going to have a 0.15 plus my Z value times my square root of my P hat, so 0.15 times my Q hat all over my sample size. Take a minute and calculate. Please make sure, what kind of rounding do we do here? We're doing 3 decimal places. The reason we do 3 decimal places is because when I get a 0.124, I can think of that as a proportion, or I could think of that as 12.4%. We always want to have that decimal on that percent. So always 3 numbers after the decimal. I think I'll be picky on this one, so be watching for that. On the other side, I ended up with a 0.176. Quick thing, because this is a proportion, it will always be less than 1. If you get something larger than 1, you messed up, right? Because if we're thinking of it in terms of percent, if you get something larger than 1, it would be over 100%. So the true proportion of men who applied is somewhere between 12.4% and 17.6% to nursing school. All right, I think you've got it, right? It's just same but different. I know that makes a lot of sense. So let's talk about sample size. So we didn't do this in 7.2, but we did in 7.1. So anytime it asks to find the sample size needed or to find the minimum sample size, things like that, we solve the margin of error for N. We did that in 7.1b. I did it for you here. So N is equal to P hat times Q hat times your Z value over E, all squared. Remember, what does E stand for? Margin of error. And typically our clue word for margin of error in these finding sample size is the word within. So be on the lookout for that. And what else do I have to do? I need to always round up to the next nearest whole number. Remember, golden rule of this is always go up. Excuse me. So let's do one quick finding sample size example, and then I promise I'll quit talking. All right, so example 711, my favorite one. Slurpee sounds good. A recent study indicated that 29% of the 100 women over age 55 in the study were widows. How large a sample is needed? There's my clue, right? That's what tells me what I'm looking for. To be 95% confident that the estimate is within 0.03 or 3% of the true proportion of women over age 55 who are widows. First of all, age 55 is extra information, right? We could say senior citizens or elderly or geriatric or whatever. But that's an extra piece of information. So I like to jot down, N usually is something I write, but that's what we're looking for. So I need to know P hat and Q hat. I need to know my margin of error. And I need to know my Z of alpha over 2. So what is my P hat? In this study of 100 women, 29%, so a 0.29. My Q hat then is the complement of that, or 0.71. Margin of error within 0.03, so 0.03 is my margin of error. And my Z value for a 95%, that means that alpha is equal to 5%. Alpha over 2 is equal to 2.5%. So I am going into my Z table and looking for a 0.0250. I believe that one's a 1.65. I hope you've got that part figured out. Nope, that's not. That's a 1.96. I hope you've got that figured out better than I do. That's what I was going to say. Just checking to make sure that you're paying attention. So my formula for N is equal to P hat times Q hat. So 0.29 times a 0.71 times my Z value over margin of error squared. So my Z value, I think, is a 1.96. My margin of error is a 0.03. You can do this however you want. I usually start with 1.96 divided by 0.03. I hit an equals and a square it, and then I multiply by P hat and Q hat. Do whatever works best for you. I ended up with an N of 878.9 something. But you all know that we can't have 9/10 of a woman over age 55, right? So what is our minimum sample size needed, or how large a sample size is needed? 879 women in order to be 95% confident that we will be within 0.03 of the true population proportion. Unfortunately, that's all I've got for section 7.3. I miss you, and I can't wait to do more notes. Have a great day. Bye.